perhaps we come across something and we know, say we've got a function, but we don't know the function, but we do know something about its derivative. That could happen, for example, we know velocity is an example of a derivative of the distance function. Well, what if we can come up with the velocity function a lot easier than we could the distance function? Is there a way that we could get from the velocity function back to the distance function? Well, the answer is yes, we can, and that is what we call doing what is known as the antiderivative. So it's taking the derivative and trying to find the function, so to speak, from which it came. That's the idea. Okay? For example, say I want to find function f, big F, that has f of x equals x squared as its derivative. So I want to find a function f that has x squared as its derivative. So in other words, if I took my function f and did the derivative, I would get x squared. Well, if you think about it, so this is the derivative. And so as we know, when I take a function and do the derivative of it, I lose a power. So doesn't it stand to reason that my big F of x would have to have an x cubed power? If this is going to be the derivative of that, wouldn't this have to be x cubed? So in other words, I have to increase this power by 1. Now what's the other thing? Well, the other issue is if it was just x cubed, I wouldn't get x squared. If I had x cubed, the derivative would be 3x squared. So I somehow need to compensate for that, and the way I do that is multiply. Here I'm going to multiply by 1/3. Take 1/3 times x cubed. Now, there's a little bit more to it, but for now, let's just talk about it. Wouldn't this be a function that would give me that derivative? What would be the derivative of this? Derivative of this would be 1/3 times 3x squared. 3's cancel. Hey, how about that? Okay. All right. So, but here's another issue, and we'll talk about what happened there in just a second. Here's another issue. Isn't there some more big F of x's that I could come up with? Let me give you for example. I also could have big F of x be 1/3 x cubed plus 1. Wouldn't that give me x squared as a derivative? Why? Because I take the derivative of plus 1, the derivative of that's 0. So that's also going to give me x squared. What else would give me derivative of x squared? X squared plus 2, x squared plus 50, x squared minus 50. Any number I put out here, plus or minus, is going to give me that derivative. So for this reason, we're going to generalize it and say big F of x is 1/3 x cubed plus some constant, and maybe we can figure out with other information what it is. But we're going to say plus c on the end is our general answer to this question. Now, for this reason, we started with the derivative, and then we got the function. For that reason, big F of x here, that's described as the antiderivative of the function we started with there. With me on that? That's where antiderivative comes in. This big F of x is the antiderivative of that little f of x we started with. It's the antiderivative because we started with the derivative and we went backwards, so to speak. We did the anti. Okay, and this is called the general. These right here would be specific antiderivatives. This is called the general antiderivative of that function right there. These are specific ones. Okay? Now, what happened when we did this? When I did get the antiderivative, let's notice the pattern here. I mentioned one thing about it, and that was I had to increase by 1. Whereas derivatives, you subtract 1, antiderivatives, you're going to have to add 1 to the power. You with me? We added 1 to the power. Now, what was the other thing? Well, the other thing was this right here. I had to do 1/3. Now, why is it 1/3? Well, the 3, notice, matches up with that 3 right there because of the derivative thing. When I multiply, bring down the power, whatever. Yeah, this matches the new power that I came up with. And that's not going to change. Because if I do the very same problem, but f of x equals x to the 4th, in the very same thing going to happen to get the antiderivative, big F of x, to do the antiderivative of that, well, I'm going to have to increase the power by 1. But then because if I do the derivative of that, I get 5x, and I don't have that, yeah. I need to divide, put in front, is basically you're dividing by 5 in front there. So divide by that very same power that you have new on your antiderivative. And then what else? Add plus c. And again, why do we do that? Well, it's because I could put any constant whatsoever I want out here, and that, if I do the derivative of that, is going to give me x to the 4th, because the derivative of the constant is 0. So whenever you do an antiderivative, yeah, we're always going to tack on a little thing we call plus c at the end, the constant. Okay? All right. So, and if you think about it, this is just the opposite of what we were doing. Because if I do the derivative of something, say I have f of x equals x to the 9th, well, the derivative is bring down the power and multiply, and then subtract 1. Right? I multiply, and then I subtract. Or I subtract and I multiply. Because it's multiply and then subtract. What do I do here? I add 1 and divide. Isn't that the opposite of multiplying and subtracting? Yes, it is. Okay. So it is it's the opposite, very opposite thing that we're doing. Add 1 and then divide by that new power. Okay? So that is that's the basic rule for the antiderivative. Let's call it the general power rule for antiderivatives. It says if you have f of x equals x to a power, then the antiderivative f of x, what do? Well, we add 1 to the power, and then we divide, take 1 over that new power, and then stick a plus c at the end. That's the way it's always going to work. Add 1 to the power and then divide by that power, 1 divided by that power up front. Okay? All right, now, words of caution here. What if I have f of x equals x to the minus 8? What's the antiderivative there? antiderivative now. And that's the thing about on this upcoming test that we have. You're going to have to do derivatives and antiderivatives, so you're going to have to keep these straight. But anyway, I want the antiderivative, big F of x. So to add 1, what do I get when I add 1 there? Negative 9? No, it's not negative 9, is it? If I add 1 to negative 8, what do I get? Negative 7. So I divide, take 1 divided by negative 7 up front, plus c, and so we clean that up. We would say it's negative 1/7 x to the minus 7 plus c. We could flip the x to the negative 7 over. That's it. All right? What about this one? So I've got f of x equals x to the 2/3 power. Give me the antiderivative of that, big F of x. Okay, well, we'll do it this way this one time. First of all, what's the power? Well, it's 2/3 plus 1, right? What is 2/3 plus 1? 1 is 3/3. It'll be 5/3, okay? 2/3 plus 3/3, that's 5/3, okay? Well, I do 1 over 5/3. Like I said, I'll do it this one time this way, plus c. 1 divided by 5/3. Now, here's the thing. 1 divided by 5/3. That simplifies. 1 divided by 5/3, or, in other words, 1 times 3/5. This is 3/5. So 3/5 x to the 5/3. See that? So what if I had, really, what you could say that is, that's the reciprocal of your power. You with me? Because if the power was negative 8, negative 7, then the reciprocal is negative 1/7. If the power is 5/3, then the reciprocal is 3/5. So it's really more reciprocal is what this is. So if I had f of x equals x to the, let's make it 7/3. And what's the antiderivative there? Big F of x. Well, it'll be, the new power would be 7/3 plus 1, which would be 10/3. What's this one, though? It'd be 3/10. I mean, you can put 1 over 10/3 if you want, but it's going to be the reciprocal. It's 3/10. Okay? Especially handy when you have a fraction. All right. So far, so good. Now, there is one, I should have written it on, talked about it maybe earlier, but there is one exception. And it comes in this power rule. Let's see, what was it? F of x equals x to the n. That is big F of x antiderivative, 1 over n plus 1, x to the n plus 1, plus c. There's one exception. Does anybody know it? Anybody see it? For this antiderivative of that to work, n cannot be negative 1. For this rule to work, n cannot be negative 1. You see why? Why it wouldn't work? Yep. It would be because this power would be 0, and so you'd have 1 over 0 here. 1 over 0, that's bad. It's undefined. So you can't use it when the n there is negative 1. No. When x is actually, it turns into, it worked into a logarithm. The derivative is a logarithm. For our book, that comes in Calc 2. We don't talk about it, but you can look it in the back. Look it up in the back. Yeah, it's actually a natural logarithm. derivative, antiderivative, I should say. But that's the only one it doesn't work for. It's negative 1 power. So yeah, if it's a negative 1 power, we have to do something different. So it won't come up for us, so that's the good news, for now anyway. If you take Calc 2, though. All right. Now, the other one I'll mention, what if I have my original function here is just a constant, 7. Well, technically, I guess, well, showing anyway, I don't. But technically, what do I have there? Wouldn't that be, if I wrote in x to a power, it'd be x to the 0 power? So what is that going to mean here? If I could write in an x to the 0 power, what would this power now be? Be x to the 1, wouldn't it? Because you just add 1 to that power, you get x to the 1. And then, of course, you divide by 1, so it's just 7x. Yeah, so a constant, the antiderivative, you just get back to the x, 7x. Essentially add an x in there, or whatever variable you want. And then add, don't forget, plus c. All right. Okay, well, what about, that's the power rules. What else might we encounter? Well, we might encounter some trig functions. Antiderivatives of trig functions. Okay, so let's say, let's just start with sine. We'll do the antiderivative. If I can spell it. So in other words, I want this function to be something that when I take the derivative of it, I get sine. What trig function gives me a derivative of sine? It'd be cosine, yeah. However, he's right. What else do I need with that? Because the derivative of cosine is not sine, it's minus sine. So if I want to come back to positive sine derivative, yeah, I need a negative cosine. Yeah. The antiderivative of sine is negative cosine plus c. F of x, so guess what on the cosine? The antiderivative is sine. Now, let's think about it. What's different about that? So sine, the antiderivative is negative cosine. For cosine, the antiderivative is sine. What's different about that? What's the derivative of cosine? The derivative of cosine is minus sine. The antiderivative of cosine is positive sine. The derivative of sine is cosine. The antiderivative of sine is minus cosine. What's different about those? The sign, the SIGN of those. It works opposite. For the antiderivative, yeah, it's true, they're opposites there, but the signs are just the opposite from the derivative signs, aren't they? The antiderivative sign is minus cosine. The antiderivative of cosine is positive sine. The derivative of sine is positive cosine. The derivative of cosine is minus. So it works, as far as if you want to look at it that way, it works opposite. Now, here's the other thing. Is there a function, is there an antiderivative for tangent, or a nice one anyway? Talking anti. Well, for this to work, there would have to be something here whose derivative is tangent. There's not a nice one where the derivative is tangent, is there? Because the derivative of tangent is secant tangent. No, the derivative of tangent is secant squared. Right? So there is one, but it's not a nice one. Okay? My quote unquote nice. Okay? It's not a nice one. All right. No, the ones we have nice antiderivatives for would be the ones like secant squared. Wouldn't it have a nice antiderivative of secant squared? What would be the antiderivative of secant squared? the antiderivative of secant squared would be tangent, wouldn't it? Plus c. With me? The antiderivative of secant squared is tangent. Why? Because the derivative of tangent is secant squared. What would be another nice antiderivative? Another nice antiderivative would be secant tangent. If I have secant tangent x, secant x tangent x, what's the antiderivative? Secant x. With me? Why is that? Because secant x, the derivative is secant tangent. So the antiderivative of secant tangent is secant. So anyway, just be aware of that. Main ones right now is the sine and the cosine. The antiderivative of sine is minus cosine. The antiderivative of cosine is sine. So the sines are just the opposite of, which makes sense. We're doing the antiderivative, so the sign should be opposite if you think about it. Okay. All right, but let's talk about a few other things here. Say I have f of x equals 10x, and let me state it just how they will state it in the book. Find the general antiderivative of this function. Okay, find the general antiderivative of the functions that I'm fixing to do. All right, so number one is f of x equals 10x. So what I had, 10x? Yeah, 10. Well, the deal is here, I've got a number in front. Does that cause any problems? Not one bit of a problem. So if I do the antiderivative, add 1 to the power, so that one's power of 1, so that would bump it up to 2, right? Then I'm going to divide by 2, basically. So I can just say 10 divided by 2 there. So it'll be 5x squared plus c. Wouldn't that work? I believe so. And of course, the check is, what's the check of this? Take the derivative of that and see if you got that, right? And it is. 10x. Derivative of c is 0 because c is a constant. All right, number 2. F of x equals 8x cubed plus 5x to the 4th minus 9. Again, find the general antiderivative. Big F of x is what we're calling it if it's little f of x to start with. Big F of x would be, so what would I have here? Well, again, the good thing is with pluses and minuses, you can just do them separately. It works real nicely if they're pluses and minuses. The antiderivative of that, what would it be? Well, I'd have 8. The x to the 3rd would bump up to the 4, so I'd have 8 divided by 4x to the 4. This one, I'd have 5. The power would bump up to 5, so I'd divide by 5. What about this one? If it's just minus 9, what's the antiderivative? 9x. And then don't forget the plus c, so it winds up being 2x to the 4th. That would be 1x to the 5th, just x to the 5th minus 9x plus c. So that would be our general antiderivative of that particular function. All right. Another one here, number 3. What if I had function was square root of x plus 1 over x to the fourth. What would I do with that? Probably a good idea to what? Rewrite these as x to powers. What would be the power of x there? Square root, the x to the 1/2. And then even here, write that instead of 1 over x to the fourth, write it how? X to the -4. So yeah, the antiderivative then, not to be confused with the derivative, we're doing the antiderivative. The antiderivative would be, add 1 to the power, so that would be x to the 1/2 plus 1, that's 1/2 plus 2 over 2, so that's 3 over 2. And then what goes in front? The reciprocal of that, 2/3. You can write 1 over 3/2, but then you'd have to turn around and simplify it to be 2/3. Okay? Plus, what would this one be? Well, add 1 to -4, you get -3. Then I divide up here by -3, so that's -1/3 plus c. So it's 2/3 x to the 3/2 minus 1/3 x to the -3 plus c, and you could write the negative power, flip it over if you wanted to. I choose not to. Okay. All right. Now, it is again important to note, just like on derivatives, if you have multiplication, you got a whole different thing. If I have f of x equals x to the fourth times sine of x. Sure, I can do the antiderivative of x to the fourth. I can do the antiderivative of sine of x, but what's the problem? If this was x to the fourth plus sine of x, no problem. Right? I could do the antiderivative is, what would that be? X to the fifth, so it would be 1/5 x to the fifth. Sine, the antiderivative, remember it works the opposite, so that would be minus cosine x plus c. I could do that. This one not so much, because it's not adding or subtracting, it's multiplying. So the antiderivative of this is not so easy. Matter of fact, there's not really a product. You know, for derivatives we had product rule. You have to do some different things if you get a product. Okay, so it's not just an easy antiderivative because it's multiplying. Same thing would go for dividing. Just be aware of that. We won't come across those yet, but just be aware. If it's multiply, the antiderivative is tough. It's a little tougher. Just like it was for derivatives. Okay? All right, so we've used here f